welcome to the ACIT Global Podcast. It's a huge honor for me to welcome Professor Karl Friston to today's episode. Karl Friston is regarded by many as one of the world's most influential neuroscientists, is a member of the Royal Society, has honorary doctorates, and I think I would spend half the podcast listing down all his achievements. I think I can cut it short by saying that you can check out his Wikipedia page or his age index, or I could say the more important thing is I also hold him in very high regards as a person, has become a scientific mentor and idol for me. And so I'm really excited to have you here, Karl, today.
It's wonderful to be here. Nice to talk to you in public for a change.
Exactly. So great. So Karl, fundamentally, I think today, what this is going to be about, of course, we would really love to dive deep into your research fields, into what you intellectually have done in the past. But then also, I think for our audience, which are to some degree quite deep already in neuroscience literature, it's also going to be very interesting what you think about the future and where the world is heading. And I would say, let's just make this a really casual conversation. And basically, I would just start with my question. I know you started your career in the area of brain imaging, or that's at least where you got your first major impact. But now you're focusing more on theoretical neurobiology and discovering like the unifying theory of the brain, the free energy principle. So could you maybe quickly for our audience explain a bit how this journey exactly looked like, going from brain imaging, but then actually ending up more towards the area of a unifying theoretical framework for human behavior and thinking?
So that unifying theoretical framework was always an aspiration since a very early age, probably since I was about 15 or 16 years of age, when I wanted to be what was then known as a mathematical psychologist. So I took the earliest opportunity that I could to get into research, and I was lucky enough to be around at the inception of human brain mapping. And there, in that field, did much of the early work in providing tools for analyzing time series from PET initially and then functional magnetic resonance imaging. But it quickly became apparent that exactly the same principles and tools that we were using to make the most sense of this brain imaging data could also be applied in principle to the way that brains make sense of their sensory data as imaged through our eyes and our ears and our skin and our interoception. So the principles were exactly the same. It was just a question of translating it to a slightly different field. And that field, of course, was the most interesting field, namely you and me. How do we work? But the maths was very, very, very similar.
So that's very interesting. So basically, coming from a mathematical background, you developed methods how to optimize the neuroscience methodology. But then actually at some point you realized in all of this data sampling and all of this, I would say, approaches to make sense of data and data richness, the question came up, hey, wait, how do we as humans actually sample this data? How do we make sense of this extremely rich environment that we're living in?
Yeah, I think that's a very beautiful way of putting it. And it also speaks to the notion that we are all little scientists, because we comply with exactly the same principles, and formally so. One of my favorite examples of that are the principles of optimal Bayesian experimental design, which is just a statement that we deploy all our sensors to harvest data in the right kind of way that's going to resolve uncertainty about our hypotheses. And you see this all around you, just in the way that I use my eyes to palpate the visual scene, or I choose which Wikipedia page to visit, or indeed which news channel or social media I select. All these are basically acts upon a world or engagement with a world that comply exactly with the same principles of experimental design in brain science in specific, but I think science in general. We're all scientists at heart.
Yeah, I think that's Piaget, right? Originally, I think he said something like that. Yeah. And then, so maybe giving our audience quickly an overview. So, I mean, you've come from I think from the Helmholtzian approach and the mathematical way of talking about the free energy principle. But in other literatures, people talk about Bayesian brain hypothesis. In yet other areas, they're also studying the really psychological aspects only without the mathematical framework behind it. So I think what is often a bit hard for people getting into like your research, maybe that it brings together so geniusly, I would say, physics, mathematics, psychology, but then also biology. If now you would say, for someone who really doesn't have a strong mathematical background, how would you explain your research in everyday experience terms, so to say?
Right, I will try and take. I'm probably the worst person to ask to do that. You could do this much better than I do. But just to highlight or celebrate that, the way that you set that up. I have a friend, Chris Fields, who says that the ambitions behind this kind of theoretical biology, is exactly to destroy any bright lines between physics, biology, and psychology. They're all the same thing. And if you can find that sort of encompassing frame with the right kind of calculus and the right kind of ideas, that's the ultimate goal. So it's just a question of joining the dots and making sure that you have the right kind of thesaurus that allows you to talk in psychological terms whilst at the same time talking about the underlying mathematics. But for somebody who doesn't do... So am I talking to a psychologist or a biologist? Or neither?
Let's do psychologists first.
Let's do the psychologist first. So sometimes we frame this in terms of the low road, which is not meant to be insulting, but is meant to contrast with the sparser physics and mathematical perspective. But the low road to understanding starts, I think, probably with the students of Plato, if not with Plato himself, through Kant and people like Helmholtz. And the basic idea here is that we have to have in mind an explanation for the causes of our sensations, so that what we see is evidence for something that might have caused that out there. And by out there, I mean beyond our skull-bound brains, beyond our sensorium, our sensory epithelia and sensations. So if I get a particular pattern of sensory input, if I have in mind, it could have been your face, and my predictions of what I would see, if it was your face, match what I'm actually seeing, I can be reasonably assured that the causes of my sensations are your face. And I can infer, literally like a statistician, that the face is the best guess, the best inference as to the causes and states of affairs in the world that I can only palpate through my senses, should that world exist. So in order to be able to do that, you have to be able to predict what you would have seen if you were right about the world out there. And that sort of notion of prediction, I think, brings with it a number of interesting perspectives. First of all, it leads you to the way that an engineer would build a system to do this kind of thing, and you get into the world of predictive coding, and over the past few decades, the notion of predictive processing, which has now become a predominant paradigm in the cognitive sciences. The other perspective on this, due to people like Richard Gregory, is that perception is hypothesis testing, so that you have, again, using this metaphor as you and me and our brains as little scientists, you have in mind a hypothesis that makes some predictions about the data, the experimental results of a particular experiment. And that experiment could be simply looking over there. And if those data confirm and verify your hypothesis, then you can commit to that hypothesis, and that becomes a belief. If you're wrong, then you'll have a prediction error. There will be a mismatch between what you predicted and what you actually sensed, sometimes known as a prediction error. And then that prediction error can then be used to improve or update your belief about the causes of your sensations. Yeah. And you can write this down in all sorts of mathematical ways, sometimes referred to as Bayesian belief updating, where Bayes is just used here as a euphemism for a probabilistic framing of best guesses, explanations that have the best way of accounting for the data or the empirical evidence at hand. The other perspective on that is that you've got in your head the capacity to generate predictions. So you've got a generative organ, sometimes referred to as a generative model, that makes your brain a fantastic organ in the sense that it can generate fantasies, or it can entertain fantasies and hypotheses about the state of affairs out there, and then test those fantasies or those hypotheses or those predictions by sampling the world, at least when we're awake. And these ideas have been used to great effect in things like machine learning, and in many senses, much like the way that the same maths was deployed to analyze brain imaging data as to understand how the brain works. Artificial intelligence and machine learning are now using exactly the same kind of principles. One way of looking at this, which is articulated nicely by my friend Andy Clark, is that this is a very much inside-out kind of process. It's not that we're just trying to extract information and meaning from our sensations, from our sensory states. It's not a sort of outside in with the world impressing itself on our brains. Our brains are much more in the game of generating in an inside out kind of fashion what we would have seen if we had been correct about what was causing the sensations.
That's actually very interesting. So basically, to some degree, we could, from this perspective, say that all our brains are actually doing are making stories or hypotheses about the world, and then uses our bodies, right? And I think this distinction already opens some philosophical issues, but uses the body to test those. So basically, if I walk up to a door, my brain, or whatever, my brain, that's, I think, the big question, like Nietzsche said, right? If I am thinking, what is the I that's thinking here? So let's just use the terminology like, my brain is thinking a door should be closed. I use my hand to try and open the door. I realize it's locked, right? So I have a prediction error. I update my model, and therefore I have to do action, which is opening the door. But basically, in your framework, that would not be like the brain, the sensation, and the action, but basically all of it is one process. Like it's all just one flux, right?
No, absolutely. I mean, that observation, which I think is extremely astute, emphasizes this notion of the brain as a scientist who's actually performing experiments. So there's a quintessentially inactive, embodied aspect to this formulation. And as you say, the same imperative underwrites both our Bayesian belief updating, our changing our mind in the light of unpredicted sensory evidence, and also the way that we go and gather that evidence. So, it does speak to this perception action cycle where both aspects, both our perceptual synthesis and our active inference, are both in the service of resolving unpredicted stuff, resolving surprises or prediction errors, or more generally uncertainty about the lived world. So I can't say it enough that that's so important, that sort of inactive aspect, that embodied aspect, is part of being a scientist. It's not just like a statistician making sense of data. That's the easy bit. The difficult bit is choosing which data that will be most informative in the sense making.
So would you then say that the claim from the psychological frame we're working on now, that basically experiencing life is being a scientist, would you say that captures it, or does it omit some parts of the equation that would be needed?
I probably put it the other way. I think being a scientist is one way of living a life. But I think the principles apply to every act. The scientific principles apply to every act. I would say that no, that would be a sufficient, if not slightly deflationary account of all our sentient behavior. It's a complete physics of sense making, active sense making, active sensing, and it is one of those, if you like, principles that does try to destroy all the bright lines between physics and biology and psychology. That all of our action, everything that is embodied, all the thermodynamics, all the information theoretic treatments of neuronal dynamics and the inquisitive brain can all be subsumed under this notion that we're just in the game of minimizing a single quantity, variously known as surprise, prediction error, variational free energy, self-information. Again, I'm giving you a thesaurus here. These are all the same mathematical quantity. And effectively, just my favorite one is, in fact, my favorite name for this fundamental quantity that we look as if we are trying to optimize through our perceptual and also active inference, is evidence, which is just the probability of getting these sensations under or given my model, my set of hypotheses about the way that those sensations were caused. And if you look at it like that, then that means that all action and perception is in the service of maximizing evidence, which just means that all I am doing to exist is just to go around gathering evidence for my own existence. And that's
exactly. And I think that is exactly where I want to go with my next question. So it's basically, I think if you think about, okay, we as humans, right? And then the question, I think the next one is maybe, do we even exist as humans, or are we just, one bigger hive mind or one bigger, entity that's trying to minimize uncertainty, which is the paper I wanted to write with you about, minimizing uncertainty as a human species. But before we go into that, I think if we just stay on the individual level, so if I'm basically, as Benjamin, I'm just like a set of hypotheses that has a body to work with, walks through the world and tries to minimize uncertainty, I guess with the final goal of surviving and fulfilling evolutionary targets, I think that vision, that picture works very well for surprise-related activities. For example, I see something weird out in nature and I go investigate what it is. Or it works very well for science or for, complex things. But then how do you bring this into like more simple everyday life experience? For example, drinking a cup of coffee, or the two of us, with not being simple, but the two of us having a conversation, right? So how do we bring it into these kind of everyday experience, which do not feel so calculated, which do not feel so much purposeful, How do we bring this purposeful, hypothesis-driven, free energy, uncertainty, entropy minimizing behavior? How do we ingrain this into this experience we have, this qualia of sometimes just doing meaningless things in the end?
I think the answer to that is the way that we hypothesize and try to explain our own homeostasis and our own reflexes. So let's just take the simplest instance of this kind of prediction error minimization, this surprise minimization, acting in a way to reverse or preclude deviations from the state that I expect myself to be in. Now, these are subpersonal expectations, so they could be just, I have a certain body temperature, and therefore my body will act not in using muscles, but will act autonomically. Well, I actually could use muscles using shivering responses and piloerection, but what I will subpersonally respond to a prediction error about my prior prediction that my temperature is 30, whatever degrees centigrade. And in so doing, I will then gather evidence. No, yes, I am a homeotherm and my temperature is at this particular set point, which corresponds to my model of the kind of temperature that I would have. But all of this is very, very subpersonal. It's all ingrained, innate, and probably largely epigenetically specified at an evolutionary scale. And then I see myself doing that. And then we move from the notion of homeostasis, which I've just framed in terms of one way of gathering evidence for being in characteristic states that are those viable states. But I can see myself doing that, and then I add a hierarchical level to my sense making, and I work out, well, there's another way to keep myself within that temperature range. So when I feel cold, I can put a coat on, or I can move indoors to be close to a fire, so that I never experience the prediction errors in the moment, but I preempt them, and that would be a form of allostasis. And you can imagine hierarchically, and then I watch myself, oh, I've just behaved allostatically. Well, hang on, who am I? And then you have the hypothesis that I'm a self, and that I myself has a body. and that these are purposes, that my behaviors have a purpose and have goals. But these are still just hypotheses. The notion that you are a person and an agent is just a fantasy that provides a simple explanation for all the sensory evidence that you see that your body is engaging in homeostasis and allostasis.
Right.
And one, if you like, very high level interpretation of that is I see myself very often planning to reduce the surprise I expect subsequent to a particular action. So that minimization of surprise in the future before something surprising has actually happened is equivalent mathematically to minimizing uncertainty. So what that means is I see myself acting as if I was curious. And then I have the notion, oh, I'm a curious thing. So I'm inquisitive. And you get now very much towards the sort of the common perception or conception of a scientist, somebody who actively designs long experiments, waits for the data, but the fact that they committed to that experiment means that they have in mind the consequences of their action. And if they have in mind the consequences of their action, then by definition, they have agency. And then if they were aware or tried to explain their behavior, then the most plausible hypothesis, oh, I am an agent. And you get to a minimal kind of selfhood, which you wouldn't find in a virus and you wouldn't find in a thermostat. But the thermostat's still doing active inference. It's still minimizing its prediction errors. It just doesn't know it's minimizing its prediction errors, whereas it may be that you and I now have an explanation as to the nature and the mechanics of that minimization of surprise or uncertainty.
The thermostats with self-evidencing stories in the end. So then that's actually, I think that really opens up now, right, the transition to like the question of the biology, because so fundamentally what we have discussed so far is we have a strive, or we, whatever story that may be, have a strive to maintain homeostasis, right? And I think if you look at the body, how immune systems work, how dopamine and neurotransmitter regulations work, the body has this desire of having stability and like being stable, right? I think this is also a really beautiful picture for the easy actions I just described before, because actually the nicest thing is to have a stable environment where you have your homeostasis, you have like maximum minimization of free energy and uncertainty, and you're basically in the end in full control of your environment, which will also mean there's a high chance that you will eventually survive and fulfill your evolutionary targets. So I think from this perspective, that works very well. Like you have your safe bubble, and then from the outside, there come some surprise factors, and you need to go investigate until, let's say, there's a danger, you investigate the danger, you understand, okay, if I build fires or if I group together with other people in nature, we can defend against dangerous animals and we can create homeostasis again. So I really see this play now of, let's have a stable base, go out and explore, come back, deepen the base. What I would like to talk about here is, though, if you look at, for example, personality research, to have something like sensation seeking, and probably I'm quite guilty of that. I'm a person, as soon as my environment becomes predictable, I feel like horrible. I feel very caged and I want to, go out and explore the world and build something new. So how do you, because I know we know from psychology that there are different, some people prefer safety and, comfort, and that's a really beautiful thing to uphold. And some people, they really just like adventure and, heroes' journeys and continuous learning. So how do we, I think the frame so far we have established really well explains the homeostasis and fixing prediction errors to maintain homeostasis again. I think this is very well explained, but how do we explain the people like me, who just would prefer to live in a different country every single day and change their jobs every second day? Like, how do we bring this into it? Because that's kind of causing a lot of disturbance to the homeostasis we usually would wish for.
Yeah, that's an excellent question. So I think the answer to that would have to acknowledge that there are different kinds of things that have this generalized homeostasis. Indeed, you could argue, and the free energy principle does explicitly argue, that to exist as something is just a definition that you found these characteristic states, and you are remaining within those states. So your very existence is an expression that somehow you have attained these characteristic states and are remaining there. So just the high road, the physics expression of this principle is the existence of a pullback attractor or a non-equilibrium steady state. And by non-equilibrium, I mean it's a steady state that you can maintain whilst open to this fluctuating, perturbing environment, ever-changing, volatile environment. However, having said that, just to be a thing may not be sufficient in terms of disambiguating or differentiating between different kinds of things. So I can be a thing like a stone, I can be a thing like a thermostat, I can be a thing like a virus, I can be a thing like a bumblebee, I can be a thing like a dog, I can be a thing like you, I could also be a thing like my family, I could be a thing like my nation, I could be a thing like my biosphere. So there are different kinds of things. And I think that the answer to your question, why is it that I am sensation seeking? Why do I like to explore? It sounds paradoxical when you first say it like that, having thought about homeostasis, keeping things within their pullback attractor or within characteristic states. But in fact, it's not at all paradoxical. It's just the expression of what we were talking about before, about being a scientist. What is a scientist? A scientist just is somebody who tries to gather evidence by resolving uncertainty by performing the right kind of experiments. So the trick is to remember that the imperatives for action are to minimize surprise. But surprise in and of itself pertains to the probability of some sensations. But before you've acted, those sensations don't exist, they're random variables. So we now have to invoke the notion of expected surprise. What is expected surprise? It's uncertainty. So that tells you immediately that we will choose those actions or certain kinds of things that are able to remain precisely in their characteristic states, as opposed to very small things that may be more liberal in terms of their internal dynamics not being very precise. But certain kinds of things like us do actually have a very precise physiology, a very precise morphology, a very precise kind of dynamics. Those kinds of things have the capacity to roll out into the future and then pick out those behaviors, choices, decisions, actions, allostatic responses that will minimize uncertainty in the future. Now, that minimization of uncertainty just is where we started. It's the expected information game that underlies the Bayesian principles of optimal experimental design. It is sensation seeking. It's seeking those sensations that will resolve my uncertainty or provide the right kind of information to find out what's behind that mountain. What would happen if I go bungee jumping? What would happen if I engaged in a relationship with this kind of person? And what's behind that door? So all of these behaviors, all these exploratory behaviors, I think are an integral and quintessential aspect of self-evidencing. And it is exactly sensation seeking that differentiates the kinds of things that you and I are from a virus or a thermostat. But the maths is the same. It's just minimizing from the high road of the physics perspective, a path or a time integral of a variational function that scores the expected surprise. From the point of view of a psychologist, it's just an expression of curiosity, a susceptibility to, or the fact that we are compelled to respond to epistemic affordances. And those epistemic affordances that will resolve uncertainty can be about states of the world. So these can be sort of responding to salient cues, signs, for example, or the title of a paper or the title of a book, for example. That tells you, if I read that book, or if I continue listening to this joke, I will learn something at the end or in the process of listening to it. But there's another kind of information game, which is not concerned with states of a world, but the parameters of our generative model, the laws and the contingencies encoded for us, for example, in connection strengths in the brain. We can also choose those actions have information gain about contingencies and laws. And this, I think, will be better understood in terms of responding to novelty. So these epistemic affordances are, in my mind and in my experience and in my maths, dominate over the sort of 20th century view of things that underwrite behavior, which would be things like rewarding or reinforcing or utilitarian measures. They're certainly important. They provide the constraints that define this pullback attractor or this characteristic set. But the way I move around those characteristic states, actively move around by sampling, is driven by this, by curiosity, by sensation seeking, literally.
Yeah. No, that's amazing. But I think then the really interesting thing here is, so basically the mathematical function underlying our, epistemological approaches is basically then the same, right? But we still have like some interpersonal differences. So basically, I think the interesting thing here is some people like to venture into the uncertainty in hope that this quest will bring them some fundamental truth about their inner states and the world, like some rules they can infer to have, homeostasis one day, this promised Neverland that you embark on a quest to find. And other people may already have found it. For example, I grew up in a mountain village originally. I have some friends who still stayed there, and I think they're really happy with their life, right? And it's kind of like they just made the map that they care about, the village and the environment, the people in there. And that's why they quicker, I think, reduce the uncertainty and only now react to maybe changes from the outside, but maintain this homeostasis. I think we are back. Yeah, should be back now. Apologies. So basically, and then, some people, they may embark on greater challenges of uncertainty to figure out fundamental rules. My question would then be, where does this difference come from? Like, where does this come from that different people seem to deal with different sizes of uncertainty? So basically, we now established that it's not two types of people fundamentally, but more like the same mathematical function expressing itself in reaction to a perception of uncertainty. But then how is it that these perceptions differ? I mean, on a psychological level, you probably can say it's genetic differences, like it's probably something like dopamine levels. It's something like, I would say maybe social factors, cultural factors. Some cultures encourage risk-taking more than others. So I think on a psychological and sociological view, we have an explanation for this. But if we really look into the free energy principle as a mathematical or biological principle, how do we explain that these uncertainties that we deal with differ like this? And I think everything else we discussed so far about the differences in behavior just stem from this difference in epistemological perceptions of uncertainty in the world.
No, absolutely. So technically, to answer your question, you would just apply the free energy principle to all the phenomena you've just described. And it's remarkably simple to do so. So I can we can just rehearse. You've answered your own question, but I'll just now rehearse it by applying the free energy principle to it. So first of all, the answer to the question, why do different phenotypes or people or things behave in a unique way? And part of that uniqueness is their balance between the epistemic affordances and these more constraint satisfying ways of minimizing surprise. So if I know that being out there in some space is very surprising, I am not going to choose those plans or actions that will cause that kind of expected surprise. So there are two kinds of expected surprise. There's the epistemic kind, and then there's this pragmatic kind, often characterized in terms of constraints. To be me, I have to be within certain temperature ranges, to be within certain places in the world, or have certain physical characteristics. So to be me, by definition, means I have to be within this attracting set that provides constraints on it. So the question, I've got both these, we now have a constrained or expected constraint plus an expected information gain contributing to the choice of behavior. And that means that any one person will make a different choice simply because they've got a different generative model, a different fantastic organ, and a different set of prior beliefs that will balance whether the constraints are more important than the epistemic affordances or vice versa. So the question now is, where does that variation come from? And this variation has to be there. It's known as the law of requisite variety, emerging from early cybernetics. It comes from many, many different levels. So how could one apply the free energy principle to that? Well, you could apply it to evolution. So natural selection, from my perspective, is just Bayesian model selection, which just means selecting those models, those phenotypes that are hypotheses that evolution puts to the niche, that this is a good fit with this niche. So that marginal likelihood, or that evidence, just is adaptive fitness. So if things are good at self-evidencing, they are by definition evincing or exhibiting high adaptive fitness, and they will be selected. In statistics and mathematics, that's known as Bayesian model selection. You have a number of hypotheses, and you score the goodness of those hypotheses in terms of their evidence or their marginal likelihood, and you select the one that you has the greatest evidence, and then you start again with the experimental design that we talked about. And evolution does that by exploring hypotheses by the law of requisite variety in terms of, say, mutations, to explore the space of phenotypes, each being a hypothesis that this is a good fit or an apt explanation of how to live in this particular eco-niche. So that's how you would apply the free energy principle to understand the emergence of heterogeneity and also convergent evolution at an evolutionary timescale. You've also brought in a really other interesting issue or phenomena or mechanism at a slightly, well, I was going to say at a slightly faster timescale, but it's not really. It's actually a mixture that couples different timescales to which one can apply the free energy principle, which is that is niche construction. So not only are we talking about natural selection as a free energy minimizing process via it being simply a manifestation of model selection, we are now in a position to note that the minimization of surprise entails a certain isomorphism or synchrony with the thing that you are modeling, which means that as you actively engage with your environment, you can also imagine the environment modeling you or learning about you in some way. And now the environment becomes subject to selective pressure. You can do Bayesian model selection on the environment, and then you get niche construction. And then you can talk about cultural niche construction. And then you are committing to the notion which you actually mentioned right at the beginning, which is the importance of lots of things all self-evidencing together that are sufficiently similar to start communicating and sharing their beliefs and shaping their environment. And from that, if you apply the free energy principle, you're now trying to look at those principles that underwrite the joint free energy minimization of an ensemble or a population or a group, a multi-agent perspective. And then from that, you can start to think about cultural niche construction as and the emergent phenomena. So each level,
and species, right? We even go to the species level, right?
Absolutely, yeah, and speciation. So but within this, of course, you've got this. As soon as you get to the level of co-construction and cultural niche construction, we get to another, which you've actually already introduced. So let me just apply the free energy principle to another source of variability in terms of whether we go bungee jumping or exploring or go to Thailand, if we're Westerners. That's age and neurodevelopment. So there's another time scale over which free energy minimization will ensue, and that's the optimization of the parameters of our generative model, these laws and contingencies that are constantly being updated to minimize surprise. That's known as learning. That occurs both, moment to moment, but also at a neurodevelopmental timescale, which means that there's going to be a progressive change in the things I choose to do, depending on upon how old I am. And what generally happens is that you can get old fast or slow. So your friends who stayed in the mountains probably got old quite quickly, simply because from their point of view, they and their particular gifted priors, gifted by evolution and cultural evolution, basically by their parents and their conspecifics and their family and their local culture. Those priors meant that very quickly, within a decade or so, they became very familiar with their lived world, which means that there is no resolvable or reducible uncertainty. So the epistemic affordances of exploratory behavior now give way to the characteristic, this is the kind of person I am and this is what I do. Yeah. But you also see that naturally during aging. So it's only young people who go exploring. Old people like me don't. We become wise and we know exactly how our daily cycle unfolds, from the cup of coffee in the morning to news at 10 in the evening. And any perturbation to that is very surprising, simply because we don't, people of my age don't have the same curiosity, because we have resolved a lot of our uncertainties about our lived world. So that will change from moment to moment as I grow older. So there are so many sources into individual variability, given that no one person has the same generative model of their uniquely experienced world that they're self-evidencing within. And that world has to change, because if my universe is constituted by other things like me who are trying to learn, then by definition, my universe is always changing. So I can't possibly have the same generative model as you would have. So, applications of the free energy principle to these different levels of surprise minimizing, free energy minimizing processes, I think can yield really interesting insights and actually tell you that intersubject, that expression of the law of requisite variety is actually an emergent property of joint free energy minimization when you start to talk about co-constructed universes.
Exactly. Yeah, and also because you, as we just said, right, in the act of minimizing my uncertainty, action will follow, as is like stated by the free energy principle. But when action follows, I will impact my environment. So I change the environment for other perceivers, which then causes prediction errors for them, right? So for example, if I take the car, right, and go to the cinema, then the person was expecting the car to be in the garage will have a prediction error, right? So basically, on our quest to update our models, we will change the world. And this change of world, again, causes prediction errors for other people, and that keeps the whole world dynamic, right, to some degree. Now, I think this is a really beautiful picture where we can think about fundamentally us all being driven, or us all being the same mathematical function, expressing itself. But then given the specific uncertainty, let's say imperatives we experience, shaped by genetics, by social experience, by upbringing and everything else, that's basically us then, right? So basically, I'm just this free energy minimizing mathematical function, given the specific constraints and factors I grew up with and I face every day. And that is causing my actions and my quality and experience of life. Is that kind of a picture that you would agree with?
Yeah, absolutely. Although beautiful. I think I'd have to ask you where the qualia come from in that.
Yeah. Actually, I want to, because since I think 10 minutes ago, I want to start with the consciousness, but I want to like wrap up all the other questions before I go there, because I think that's like the peak, I think, of the podcast. So I think one thing, just two things I want to wrap up, and then we jump to consciousness. And trust me, that's been burning in my throat for the last 10 minutes. One is actually just a bit technical. So I just keep reiterating these things because, I think our audience, for me, myself, when I read the free energy principle, I was really attracted by its simplicity. And then over time, I started like, it cannot be so simple, then you dive into biology and you like realize, no, actually it is. You go into psychology and you think, oh no, but people are so different. But you understand actually a lot of actions, for example, also cognitive biases, cognitive dissonance, which are like some of the most well-studied phenomena in psychology. You can also very well explain them with uncertainty reduction in the end, or with self-evidencing and telling a story about yourself in the case of cognitive dissonances. So I think then just really one technical question, more like out of self-interest also. I originally come from behavioral economics research, more like looking at dopamine circuits and like valuation in the brain and like cognitive biases. So I know in the literature, there was always a big talk about utility functions, like what do people value, how do they draw their functions? Just to be very technical, would you say in the free energy principle, the utility function, if we talk it mathematically, can still be individual, or would the utility function always be the same and we just express it differently through our environments and constraints?
I think it would have to be different for every individual.
Right. Okay.
So the utility function is a special case of the constraints that I was talking about before that are definitive of thingness, the constraints on states of being. So, in economics, I would have, I would implement utility very much in the spirit of homeostasis as wanting to have a sustainable degree of wealth. But notice the sustainability is important here. It's not about maximizing utility. It's not about, it would be very surprising if I got incrementally richer and richer, and that would not be a good thing. What is a good thing is a sustainable, comfortable degree of wealth that would be characteristic of me as a wealthy, happy person. So you can write that in as a constraint. I think the slight problem with utility theory and sort of reinforcement learning and behavioral psychology is it's too monothematic. They assume that there is a single dimension labeled reward or cost or a loss function or utility function that can be reduced to a single dimension. The physicist would just smile at that and say, no, that's not right. If you just look at things like the constrained maximum entropy principle, what we're talking about is an exceedingly high dimensional set of constraints that apply and define this kind of thing, which means that your utility function has as many dimensions to it as there are attributes of the thing at hand. So you'd have to define your utility in a very high dimensional way. And that's just the expected cost I mentioned before. So the expected free energy is equal to expected information gain minus expected cost or plus expected utility. If you score utility now as the surprise or the inverse surprise as the log evidence of being in this particular outcome or this state if I pursue this action. So I think you can gracefully absorb utility theory, but you have to make it quite a profound move. You can no longer have just one monetized or one-dimensional utility function. It has to be a multidimensional object.
So it's basically this fundamental free energy function, right, which underlies all of existence, expressing itself in like our individual bodies and our actions being determined by a highly multidimensional utility function, let's call it, subject to like a lot of variety factors, not just, economic utility, of course, but like a huge variety. So basically a function within the bigger function in the end.
Yes, absolutely.
Yes. Beautiful. And then to stay on that, just one question. In mathematics, you always have this question, is math something representing, is it a picture of reality or is it actually representing reality? I know it's a very metaphysically loaded question, but if you would just briefly answer, do you believe this free energy equation, does it represent the actual structure of the universe, of existence? Spinoza call it substantia causa sui, other people call it God, other people, Nietzsche calls it will to power. Like, would you say this free energy principle in your mind is this kind of, I would not even say spiritual, but this kind of like unifying physical real entity, or do you think it's just a really strong mathematical like photograph of what's actually the underlying force in the universe?
I can't answer that question with any authority, but my suspicion is, I'm afraid, it's probably more like the latter. For me, maths is just the best language, and language is a way of articulating these fantasies. So I think that all of physics is just a fantasy, but there is nothing else. So if you accept that all fantasies, models, hypotheses are wrong, but there's one best one. And that best one is the one that has the greatest evidence, which just simply means mathematically it provides an accurate account of everything that is measurable or has been measured. That is minimally complex. So here's this huge
exactly.
So in that sense, the free energy principle conforms to itself, much like natural selection, in the sense that theories of selection have themselves been selected and evolved. The free energy principle also conforms to itself, that it is a simple hypothesis. But almost by definition, it doesn't purport to have any sort of metaphysical reality to it. It's just a description of the way, the way that we can understand and describe ourselves.
I see it very different. I also like, I have a very similar view to that. So I also believe, like, it's fundamentally, I think, mathematics, physics, and neuroscience as well. I think it's really good pictures of reality, but I think it's just the best ones we have because they're parsimonious, they're like very explanatory, but then probably still for the big questions of life, we cannot just look at maths, we still need philosophy and I guess religion as well. That's, I think, also like a nice kind of view on it. And then maybe just quickly, if you tell about, this storytelling. So now we just said, okay, math and physics are also stories, just probably the best stories that we have to explain the world. I'm just thinking about something now, and then we go to consciousness in a second. Something like Harari's theory of evolution, that basically all that humans are doing better than animals is storytelling. And that's kind of like how evolution could have worked for humans. And then also something like, Dawkins' distinction of like memes and genes, like kind of like this idea that we don't just pass on genetic information, but also cultural. So from that perspective, then, if we see storytelling on this kind of like human level, this collaborative level, would you then say, and also thinking about something like embodiment, I would argue that if you use your iPhone to store the memories in your brain, in your phone, it kind of has become a part of your system, right? So actually the self is not constrained to just the physical body I was born with. I can expand it with the knowledge of networks I built with phones and with all such things. So my question then, if you quickly think about the memes, if we think about the storytelling of Harari's evolution approach, if you think about embodiment, does it even make sense then to talk about individuals first if we talk about free energy principle, like, going from the cells and then from cell organization to the individual, or would it not make more sense to explain our actions and behaviors more on a group level, or even on a planetary level, or even bigger than that?
Well, that's another wonderful question. I think the answer, which I'm sure you know, is yes, you should be able to apply it at all levels contemporaneously. So this is the notion, if you're an evolutionary biologist, that there is no single unit of selection. And that would happily accommodate evolutionary psychology and cultural evolution of the kind that we're talking about, that would subsume memes and language and communication and social norms and all of those things and all the geontic cues that we build around for ourselves. So I think from the point of view of the free energy principle, you've just stated it, that the free energy principle is just a principle. You have to actually apply it. It's just a method. So you have to say, where are you applying it and at what scale? And it should apply uniformly to small particles, to cells, to organs, to phenotypes, to conspecifics, again, to the biosphere at a cosmological level. So you should be able to find the same maths and the same, usually cast in terms of Lagrangian, the same dynamics at each scale when you course grain from one scale to the next. So formally, you would use something called the renormalization route to do that. And in doing that, it's relatively simple to demonstrate that there is a free energy minimization that is apparent at all these different scales. So what that means is there is always an interpretation in terms of applications of the free energy principle at different scales. So my brain cells are smart, but they're not as smart as me. So if I put my boundary that separates the thing from everything else around my brain, I'm encompassing tens of billions of smart cells into a smart brain. And if I put my boundary around my city, I'm now enshrouding thousands, if not hundreds of thousands, of smart brains into a smart culture and a smart community. So you should be able to apply the maths at each level of self-organization. What tends to happen, and this is quite important from the physics point of view, and possibly even a biological point of view, as the scale gets bigger and you have these boundaries of boundaries, things of things of things of things, things get bigger, but they also get slower. So that has the important implication that things become slow and very precise, as opposed to things that are very, very small, which are usually much more random and hotter and faster. So think about quantum physics, or sort of very fast fluctuations, that are effectively thermodynamically very hot kinds of things, as opposed to the same kind of mechanics, but just much slower and more precise, that would describe the orbiting of heavenly bodies in the cosmos. But you should be able to find exactly the same self-evidencing like description of behavior. Having said that, I do think there's a privileged Goldilocks zone for the kinds of things like you and me that do this deep planning into the future, that do this sort of that show this kind of curiosity. I repeat, a thermostat is not curious. The tides are not curious, the moon's not curious, but they can still be described as maintaining some kind of non-equilibrium steady state, and they still have orbital and quasi-periodic attractors. So they still have a description, provided you can separate the thing from everything else in terms of a free energy minimizing process, but of a particular kind. So there are lots of processes like evolution and like the weather that don't have the capacity that you and I have, which is to sort of transcend the present and think about the consequences of our actions. Evolution doesn't plan, but you and I do, certainly.
We do, exactly. Yeah. No, that's beautiful. So, and that's actually really, I think it's a perfect going to the final question. So basically now we discussed, right, everything is governed by the cell mathematical equation. Sometimes this equation takes a utility function at the initial level, which we then experience, or which then causes the perception action, I would say, unity that that constitutes our lives fundamentally. We can apply this formula, on a hot and fast level to the quantum level, then a little bit more cold and a little bit colder and a little bit less fast on the cell level, and so forth, right? Well, there's atoms first and then cells at some point after molecules. And then you have humans, or life forms like plants, animals, which again have less hot area, but still bit more fast. And then you go to planetary systems and even beyond that, where you have very slow models, but you're still actually following basically, the rule of minimizing free energy, because if planets have too much uncertainty, they might start crashing into each other, cause supernova and everything else. So now we have this beautiful physical and biological model, how everything works together physically, like an apparatus, like a machine, beautifully drafted. I mean, Einstein and Spinoza, I think that's what really their big love was, that everything has these clear structures. But I think then, and that was also why Einstein, I think, was not a big fan of quantum physics, because it brings in the randomness. But now in all of this beautiful structure, how do we explain then the emergence of consciousness? How do we explain that suddenly we have this self-perception and this kind of feeling that we are we? And why do stones not have it? Why do thermostats not have it? If like planets, if cells, if they all apply active inference, if they all try to minimize uncertainty, why does it seem like only us and probably some animals do exhibit consciousness?
Because we're very special. And it is exactly being in that Goldilocks regime of a particular size, which is well bigger than the quantum fluctuations, but much smaller than a cold universe that the moon inhabits. But in that Goldilocks, in that particular scale, we have the opportunity to do what we're talking about. In fact, you were talking about it a lot, which was this sensation-seeking planning. You can't be curious and sate your need to resolve uncertainty conditioned or consequent upon an action unless you have a generative model that can predict the consequences of action. So immediately you're talking about a very special kind of thing that has a model for which the thing is seeking evidence that entertains the consequences of action in the future. So immediately we've got now a temporally deep kind of generative model, which a thermostat wouldn't have. You might argue that a plant might not have. I'm not so sure about that, but certainly a stone wouldn't have. So I think that tells you an enormous, well, just having a generative model of the future tells you a lot. First of all, we are freed from any sentient representation subpersonal, mathematical of the moment, and we're now representing trajectories and paths framed in terms of temporal thickness in philosophy by Jerry Edelman as the remembered present. That's one thing. But notice it is a future that is unique to one thing, namely the policies enacted by this thing. So you now are licensed to use the word agent. You can't say self at the moment, but certainly by definition, what we are talking about is something that has a minimal agency. And now all you need to put on top of that is an extra hierarchical set of hypotheses or models or explanations that provide, use the word, I think, expertly, the parsimonious explanation. So that complexity minimizing aspect of self-evidencing is just Occam's principle. It's just finding those most parsimonious explanations. So if I now see myself as behaving as an agent, and I now have the hypothesis, oh, I'm an agent, then that's a very parsimonious description that accounts for everything. And then that just provides evidence that I am indeed an agent. And I now know I'm an agent. And then if you get even further into that, you can now have metacognitive sort of elaborations of this by increasing the hierarchical depth. The question you have to ask, though, when you tell that story is what will support a hypothesis that I am an agent, in the sense that just adding another hierarchical level to my generative model actually increases the complexity. It increases the degrees of freedom. So there must be something that I get by knowing that I am a me in a particular state. You know, I could be in love, I could be very angry, I could be embarrassed, I could be frightened. There has to be something that I get that provides a more parsimonious account of my engagement with the world, that is conditioned upon and can be acted upon, given that I now can recognize I'm in this state. And a lot of people that I speak to in neurophilosophy and elsewhere would say that that kind of ability to recognize I am me in this state is necessary to deploy attention, to select internally the sources of evidence and ignore the sources of evidence that would be appropriate for the context that is implied by I am in this state. I am frightened, I am in love, I am hungry. All of these have very useful, coarse graining the states of being, freeing me from dyslexithymia or alexithymia and enabling me to recognize I'm in this state or that state. Allows me now just to focus in and not actively go and get information, but attend to the right channels. So this is like a mental action on the inside, a covert action. So I think that the bright line that distinguishes me from me and those animals that have this kind of minimal selfhood and sense of agency, I think that bright line is the fact that they are able to recognize that they are agents in a particular state and thereby act on their sense making and evince these internal actions, which a psychologist would call attention or sensory attenuation. And I think that would be where I would look for why we are special kinds of creatures.
And that's actually fascinating. So basically all this consciousness, all this thing that, the rationalist philosophy has like prison as this, pinnacle of existence in the entire cosmos. It's basically just that our buildup, our biological buildup is such that we have internal states that are kind of feeling in a way like hunger, fear, pain, happiness. And because we have these impulses, somehow our free energy principle, our free energy equation starts to tell a narrative that this must be an agent. And that means that consciousness just basically arises from the simple fact that we are at the exact right position between quantums and like galaxies, the exact right level of complexity that embodies, let's say, animal kingdom, humans, and then potentially plants. We are just at the right level of complexity above cells, but below groups and nations and companies, that we need this kind of storytelling of a consciousness to reduce the uncertainty given our specific constraints.
I think it's absolutely right. And notice you use the word our about 5 times there. So I think the fact that our universe is made up of things like ourselves is absolutely crucial for this kind of emergent complexity that's always chasing the accuracy to minimize the evidence or the free energy. You won't find the moon. The moon doesn't have many sisters. Whereas I'm sure you and I, well, in fact, I've only got brothers, but I'm sure you have sisters.
I do. No, Karl, thank you very much. We're already at the end of today's podcasts. I can definitely imagine the audience will love to hear a follow-up podcast, but we can align on that later on. For me, really, all I have to say is a big thank you for taking the time for today's podcast. I think it was a beautiful journey throughout the layers that this free energy principle can be applied, from neuroscience to genetics to like our everyday experience, all the way up to like the cosmos. So I put my background picture, I think, in good preparation of that. And so fundamentally, Karl, really like a huge thank you for being here. And yeah, I think our audience was very honored to have learned from one of the most influential thinkers of our time. Thank you very much, Karl. Thank you.
Thank you. Very great to see you.
Thank you so much. And well, hopefully see you soon again.
I'm sure we will. Bye-bye.